Hello everyone. So in the today's session, we are here to discuss about the concept of logic gates. So firstly, we discuss the concept of logic gates from the basic concepts. So what is meant by gate and what is the logic gate? Like that, we will discuss starting in the basic. So gate in the sense. So what is meant defined as a gate? So gate is an electronic circuit. Gate is an electronic circuit that performs the basic operations on the electrical signals, right? So it is a generalized definition given. So gate is an electronic circuit that will be able to perform the different operations or the basic operations what we require on these electrical signals. So then when we come across what is meant by logic gate. So this logic gate is defined as it is also a digital circuit. It is also a digital circuit that performs the logical operations. This point is very, very important, right? What is logic gate in the sense? It is defined as a circuit that performs the logical operations between the binary digits. This is very, very important. Between the binary digits. You can call these as your bits also. Okay. Binary digits. That is anything but your bits. Okay. Right? So you can call them as bits also. So how can you define this? The logic gate is defined as the circuit that performs the different logical operations between the binary digits and generates the constant output. Okay, and generates the constant output. That may be the output may be differ for each and every operation. So as we having several types of logical operations, we consist each and every gate separately for each and every operation. Therefore, uh, we have written the word like it generates the constant output. So, constant output in the sense for each and every gate, the functionality is different and it generates its own respective output, right? So, how can you define the logic gate means? A logic gate is defined as a circuit that performs the logical operations between the binary digits and generates the concerned output. Okay. Now, if you see, uh, so how can you describe the behavior of the gates or how these gates can behave while in the designing of the digital circuit? So, generally, we can use these Boolean expressions, right? These gates uses the Boolean algebra. That means a mathematical notation for expressing the two value. That means if at all if we have an expression with us, a Boolean expression with us, and if we want to represent that Boolean expression where we need to analyze the entire functionality of the circuit of the particular function, then we can use these gates. Okay, so these the gates can be used, or these gates will help us to analyze the functionality of the circuit, right? Likewise, we can call them as the logic diagrams also. So like logic diagrams means pictorial representation of the circuit where each gate has been its own symbol, right? As well as that particular circuit can be analyzed by using truth tables also. So how can you say that here? So generally, uh, these Boolean expressions can be represented with the help of logic diagrams, where these logic diagrams consist of the truth tables. That means, in the case of Boolean expressions, we can use these gates, where these gates help us to analyze the functionality of the equation or the function given for us with the help of the logic diagrams. And for each and every logic diagram, there will be a particular truth table where this truth table will show all the possible input values with respect to their own output values. That means for each and every input combination, there will be a respective output, and that output will be clearly shown in the truth table. Okay, so like this, you can analyze the behavior of the gates. So now, when we go to the in detail of this, then what is a logic gate? Just we will have a small overview here again. So the logic gate is nothing but the gate the gate which performs the logical operations. I have already said we have 7 types of logical operations. Just to make a note this if you require. First one is not gate, that means not operation. Next AND operation, OR operation. Likewise NAND, NOR, and then XOR, XNOR. Totally we have 7 types of operations, and for each and every operation there will be a respective and separate gate, right? So for each and every separate gate we will have a separate what means separate operation, right? So for NOT gate we will have a NOT operation. One for AND operation we have AND gate. OR operation we have OR gate. Likewise for 7 different types of operations we have 7 different types of gates. Okay, so first one is AND gate or NOT gate, AND gate, OR gate. So all these three comes under the category of basic gates. It is very very important. Among all the 7 gates, which gates are called as basic gates? In the sense NOT and OR are your basic gates. Next, NAND and NOR, these two are the gates which you call them as your universal gates, okay. And the next last two are XOR and XNOR, which you called as exclusive gates or modified gates, okay. You can represent this XOR as EX hyphen or you can write like this also, or else you can write simply as capital X OR. Both are same. XOR, you should read it like XOR, where this EX indicates your the term called as exclusive, okay. It is your exclusive. Likewise XNOR also you can make it as EX hyphen NOR XNOR, or else you can simply write as capital X NOR XNOR, okay. Total we have 7 types of gates: and NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate. Among these, the first 3 is your category belongs to the basic gates, and the next 2 are the belonging to the universal gates. The last 2 your exclusive gates or modified gates, okay. Then next we will see each and every what you say gate in detail, okay. Next, see, first we will see the concept of NOT gate. So generally the NOT gate is nothing but the NOT gate accepts only one input signal, either 0 or 1, and returns the opposite signal to output. That means, suppose if you, so this is the symbol of the AND gate, sorry, NOT gate. This is the symbol of the NOT gate. So this is the symbol, right? Suppose at your input side, if you are supplying 0 as your input, then it will generate 1 as your output. If you supply 1 as your input, it will generate 0 at your output, okay. It is nothing but it performs the concept of complement, okay. If you supply A as your input, then at the output it is taken as A bar, okay. So what is the expression for not gate? In the sense, you can take any expression here, not only x, you can take y, f, whatever it may be. So the output expression, if I take y, then y is equal to a bar, okay. Y is equal to a bar. So why I'm writing here a? Why? Because the input given at me is a. Suppose if I take input as y, then I should write y is equal to y bar. Suppose if I take x, I should write like x bar, okay. So whatever the literal that you take at your input side, that should be mentioned at your output, okay. As I am taking x, a as my input, then at output x equal to out input a, and that is to be complemented by, because it is not gate. So this is the expression, Boolean expression, okay. This is the expression. And now after writing the expression, we need to draw the logic diagram. This is the gate symbol, and then we should draw the truth table. What is truth table? Truth table is a table that consists of inputs as well as their respective outputs. So here I am having inputs A and output as x, right? So if I take input as A as 0, my output will be 0 complement, that is 1. If I take 1, that will be 1's complement, that is 0. So the opposite values of inputs will be your the outputs of NOT gate, okay. Now, next we will see the next one. It is AND gate. So the second one is AND gate. So what is AND gate? The AND gate accepts two input signals. In previous slide, we have seen the NOT gate which accepts only one input, right? Why? Because one input is enough for us to complement. But as we said that AND is nothing but, it is nothing but a multiplication operation. It is nothing but a multiplication operation. So in order to perform the multiplication, we need minimum 2 bits. That's why it take two inputs as two input signals, right? See, sorry, just I will make clear. It's okay. So it will take two input signals. So I am having two inputs here. See, A comma B. So this is the symbol of AND gate. We are having two inputs. One input is A, one input is B, and my output is X. Okay, then what is the output expression for AND gate? The output expression X is equal to first input A dot is nothing but into A into B. Therefore, X is equal to A into B is the output expression for AND gate. Okay, so you write X as your output column. Now, as we have n number of inputs, n number of input literals, then you will have 2 power n combinations. Likewise, I am having two inputs here, A comma B. So substitute 2 here, then I will get the answer as 2 square is 4. I will have 4 combinations. What are those 4 combinations? 0 0 combination, 0 1 combination, 1 0 combination, and 1 1 combination. Total we have 4 combinations, and for each and every combination we need to perform multiplication, right? 0 into 0, 0 into 1, 1 into 0, and 1 into 1. Just it is nothing but the multiplication. So here we are having 0 into 0, output will be 0. 0 into 1, again 0. 1 into 0 is 0. But only in the last case, we are having two ones. So two ones is multiplied, then we will get 1 as the answer. Likewise, we need to create a truth table. Okay, next. Next, OR gate. The third category is your OR gate. Here also the minimum requirement is 2. One is A and second one is B. But OR is nothing but it is the operation of addition. It is operation of addition. So adding of bits. In the previously AND gate is nothing but multiplication of bits, and now it is adding of bits. Okay. Now, as we are having two inputs A and B, and I took my value X as my output, Therefore, how can you write the final expression X equal to addition of 2 bits? Therefore, the output expression for OR gate is X equal to A plus B. Okay. So again, I took here 2. So as I'm having 2 literals in my input, I will have 2 power 2 combinations. 2 power 2 combinations. 2 power 2 in the sense I will have 4 combinations. I will have 4 combinations. What are those combinations? 0 0 combination, 0 1 combination, 1 0 combination, and 1 1 combination. Right? So 0 plus 0. It means you need to perform addition between those two. So add all this. Right? So when you add these, what is the result you will get? If you add 0 plus 0, you will get 0, that you know. If you add 0 plus 1, you will get 1. If you add 1 plus 0, you will get 1. But in the case of last one, 1 plus 1, in Boolean algebra, when you add two ones, always output will be 1. Whereas in the case of a binary addition, if you add 1 plus 1, in the case of a binary addition, if you add 1 plus 1, you will get some 0 with carry 1. You will get some 0 with carry 1. But this case is different and this is different. This is nothing but it is your binary addition, but this is Boolean algebra addition, performing of OR operation. So when you add 1 plus 1 in Boolean algebra, always your output will be 1. Please make note of this. Okay, next we'll go to the next gate. So till now we have seen 3 different gates. First one is NOT gate, where NOT gate consists of only a single, see, NOT gate consists of only one input, that is A. Why only one input? Why? Because one input is necessary for this gate in order to complement this. So what is the function depending here? What is the operation going on here? X is, this gate is taking input and then it is complementing the input. So when you give A as your input, you will get A bar as your output. Okay. So for a single letter, we will have only two combinations, right? That is 0 and 1. So if 0 is given as input, 1 is taken as output. If 1 is given as input and 0 is taken as output. Okay, just complementing the input values, right? Likewise, in AND gate, already I said that AND is nothing but the concept of multiplication. AND operation is nothing but it is nothing but the complement, sorry, the operation of multiplication. So in order to perform the multiplication, minimum we require two inputs, right? That's why this is the symbol of AND gate, and I given here input A and input B on the left hand side, that is input section, and I took except my output section, that is right hand side. Okay, now what is output expression? How can you define the expression? This x is nothing but it is a multiplication of two inputs. That's why x is equal to a dot b. A dot b in the sense a into b. So for two inputs we have four combinations 0 0 0 1 1 0 1 1, and if you start multiplying them, then you will get the values of x like this. Okay, and then OR gate. OR gate is nothing but addition. Here we see multiplication, and here we will go with the addition. So what is the equation here? X equal to a plus b. Why? Because we are performing addition between the bits. Here also minimum we require two bits to perform the addition. That's why we took a comma b as inputs and x as my output. Therefore, what is the equation of x? X is equal to a plus b. So what is the output expression of OR gate? Means a plus b is the output expression of OR gate. That means addition of inputs. So when you add these two, 0 plus 0 will get 0, 0 plus 1 will get 1, 1 plus 0, 1. In Boolean algebra, remember that when you add two ones, you will get 1 as your answer. Okay. So these three are your basic gates. Now we will move on to the concept of universal gates. So what is a universal gate? First one is NAND gate. So NAND gate is a universal gate. So what is in by NAND? Already we have AND here. See, so already we have NAND. Just I will explain. See here, NAND is nothing but it is a word consisting of AND, right? So it is nothing but the AND gate is being complemented. The value of N is nothing but not plus AND. It is a short form. See, NAND is nothing but not that is being added with AND. That is being added with AND. So this N and this AND totally we find as NAND gate. Okay, that means it simply resembles the operation of complementary AND, right? See, the gate symbol is same as AND, but we will find a small bubble here. This bubble represents the complement, or this bubble represents the not operation. Okay, whenever you find a bubble, it means that there will be a complement in the expression. See, first what I have said there, AND. So what is AND? A into B, that is AND. Multiplication of A and B is AND. And this AND is being linked with the not. Therefore, A into B whole bar. See here, bar is there. So A into B whole bar is the expression for NAND gate. So what you will do here, same concept 0 0 0 1, and this will be changed. These four will be same. Okay, these four will be same. Okay, because we are having 2 bits at input side. When we have 2 bits, obviously we will have 4 combinations, right? Then what is the equation of x here? What is the equation of x for us? A into b whole bar. So what we have to do here, we need to multiply 0 with 0, and then the answer will be 0, and then the answer will be 0, and this 0 is to be complemented. So 0 complement is nothing but your 1. Ever solve that? Likewise, multiply this 0 with 1, again you will get 0, again you will get 0, and again 0 complement, it is your 1 again. Here also 1 into 0 is 0, 1 into 0 is 0, again 0 complement, you will get 1 as answer. Last one, 1 into 1 is 1, and 1 complement, that is equal to 0. So 1110 is the answer what you are getting it. NAND gate output expression. See, simple, just to multiply them and put an bar over that. Okay, if you got 0, when you multiply A and B, put bar here, then you will get 1 as your answer. Suppose if you multiply A into B, you got 1 as your answer, put complement here, then that will be becomes 0. Okay, right? So if you remember this, then that will be easy for you to understand. Okay, remember that NAND gate is the gate which is performing entirely opposite operation of an AND gate. Okay, in AND gate, if you observe the truth table, you may get the value set as x value as 0, 0, 0, 1. In AND gate, if you observe the value of x, we will get the values of 0001. And for NAND gate, just opposite of these values. We got 0001, and now we will get 1110. Okay. See here, suppose if this bubble is not there, then this will be NAND, a small AND gate. For this AND gate, if you add a bubble here, that will become your NAND gate. Okay. NAND is nothing but not plus AND gate. Okay, and if you take an AND gate and that AND gate is being linked with a NOT gate, then that will become your NAND gate. Okay, fine. Next we will go with the next one. That is your NOR gate, right? NOR gate. This is also the same concept. Divide this like this. An OR gate is being linked with the NOT gate. See, suppose if this bubble is not there, this is the symbol of OR gate. Yes, if you add a bubble at your right side and then output section, then you will get A plus B whole bar. A plus B whole bar. Same. When you add 0 plus 0, you will get result as 0. 0 bar. That is 1. Again 0 plus 1 is 1. 1 bar. 0. Again 1 plus 0 is 1. 1 bar. Again 0. Here also 1 plus 1 is 1. 1 bar. You will get 0. That means this NOT gate, say this NOR gate is nothing but it is performing purely the opposite operation of OR gate. In OR, you will get answer as 0 to 1, right? In OR gate, if you observe the section of X, you will get the answer like this. So if you reverse these values, you will get this, right? NOR gate is the gate which is performing the entirely reverse operation of OR gate. NAND gate is the gate which is performing the reverse operation of AND gate. Okay, just to remember that. Next will be the last two. What are nothing but your XOR and XNOR gates, right? XOR gate. So here XOR gate is nothing but see the symbol of XOR gate is first you draw one OR gate. First you draw the symbol of OR gate. Take output some with some literal X or Y, whatever it may be, and you just add one more line in the input section like this, and now supply inputs like this. So this will be the symbol. You take this as A and take this as B. Okay, so this is the symbol. Okay, and mathematical symbol is nothing but take a plus and put this plus in a circle. This is the symbol. Okay, A X or B. This is the output expression. Okay, what is the equation of X is nothing but A is equal to, see here, A XOR B. What is symbol of XOR is? This is the symbol of XOR. Okay, so what is the condition here is when both the inputs are equal. When both the inputs are equal, then your output will be 0. See here, when A and B are equal, output is 0. Likewise, when A and B are equal, output is 0. Okay, remember that if both inputs are same, then output is 0. Otherwise, it will be 1. So in the first condition and in the fourth condition, we have outputs equal to same. We have same outputs. At that condition, okay, see, this is the first condition we are having two equal inputs. This is also condition we are having two equal inputs. For these two conditions, we got 0 as the answer. In rest of all conditions, we will have 1 at the output. That is the condition here. So what is the original expression is? Original expression is A bar B. This is also very, very important. A bar B plus AB bar. It is very, very important. What is the original expression of this XOR is nothing but A bar B plus AB bar. That means until unless if you know this expression, you cannot fill up these values, right? You cannot fill up these values. Why? Because if you substitute these combinations in this expression, then only you will get the values of X, right? So please make a note of this. This is the original expression, X equal to A bar B plus AB bar. This is the original expression, right? And then we will move to the next one, the last one. The last one is XOR gate. Okay, XOR gate. Same, you draw an XOR gate and just add one small bubble here. Okay, XOR is nothing but opposite of XOR. So in XOR, what I have said, when we are having two same equal inputs, that means 0, 0, 1, 1. When we are having two same equal inputs, then there we get 0 as an output, but here we will take 1 as an output. Okay, in the previous XOR gate, what I have said, when two inputs are having same values, then output will be 0 in the previous condition. But in the now, what we are saying, when we are having two same equal inputs, for this gate, output will be 1. In rest of all conditions, output is 0. Okay, the opposite of the previous one. That's why we fix a small bubble here. A small bubble here. Then what is expressions? What is symbol? There XOR symbol is plus is taken and put in a circle. That is symbol of XOR. And what is symbol of XOR? Put a dot here and put in a circle. That is a symbol for this. See here, this is a symbol. Now, what is the original expression for this? That is nothing but A bar B, A bar B bar plus AB. This is the original expression of XOR gate. The original expression of XOR is A bar B plus AB bar, and the original expression of XOR is A bar B bar plus AB. These two expressions are very, very important. Please make a note of this. Okay. So by this, we have completed the 7 different gates. First one is NOT gate, second is AND gate, third is OR gate, fourth is NAND gate, fifth is NOR gate, sixth one is XOR, and seventh one is XNOR. Okay. So we have seen these different gates along with their symbols, right? And among these 7 gates, AND gate, NOT gate, OR gate are your basic gates, right? And then NAND and NOR are your universal gates, and XOR and XNOR will be your exclusive gates, or else it is called as a modified gates. Okay. So if we have a small review of this, see, a NOT gate inverts a single output. That means 0 is given, it is taken as 1. The AND gate produces 1 if both inputs are 1. That means when A equal to 1, B equal to 1, then 1 into 1 you will get 1 as answer. That is given here. Next, OR gate produces 0 if both input values are 0. That means 0 plus 0 is equal to 0. That is, it is saying here. Likewise, XOR gate produces 0 if the input values are same. It's very, very important. For XOR gate, when input values are same, the output will be 0. For XNOR gate, reverse of that. When input values are same, output value is 1. See here, if inputs are same, here it is 0, but here it is 1. These two are opposite to each other. Next, NAND gate. NAND gate produces 0 output if both inputs are 1. Okay, right? It is nothing but opposite for AND. If you observe these two statements, AND statement and NAND statement, the two, here 1 is there, here 0 is there. Likewise, NOR is the opposite of OR. If you observe the OR statement and NOR statement, see here 0 is there, here 1 is there. That means NAND gate and gate are opposite to each other. OR gate, NOR gate are opposite to each other. XOR and XNOR are opposite to each other. Okay, this is very, very important. See here, and NAND are opposite to each other. or NOR are opposite each other, and these two are opposite to each other, and this is separate, right? And these three are your basic gates, these two are your exclusive gates, and these two are your universal gates. Okay, right? So by this, the explanation of digital logic gates is completed. So please, you don't think that only a gate consists of two inputs. That is not the condition. A gate can consist of n number of inputs, but the minimum number of inputs will be two. Maximum number, that depends on our own. Okay, just I took a small example for three inputs, A into B into C. So for three inputs, I will have 8 combinations. For n number of inputs, I will have 2 power n combinations. Likewise, for three inputs, I will have 2 power 3 8 combinations. So I return the 8 combinations here, right? And then I have written the values regarding here. So as it is an AND gate, I will multiply A into B into C. This is the expression for output expression for this particular gate. So when I will get x equal to 1, whenever all the inputs are high, then only output will be high. See, already I have given here, see, an AND gate produces the output 1 if both input values are 1. Both in the sense, if you have 2, if we have 3, all the 3 should be high. If you have 4, all the 4 should be high. Likewise, as I am having 3 here, if A equal to B equal to C equal to 1, then only our output will be 1. See here, the last combination A equal to B equal to C equal to 1, then only I for output as 1, right? So that is a condition. Please remember that minimum number of inputs for a gate will be 2. The 2 except not gate, and the rest of all gates will be 2. The maximum number depends on our own expression. Okay, thank you.